Hey everyone, in the previous video we were talking about the concept of isomers. We said that isomers are compounds with same molecular formula but different structures. They have the same number of atoms but the arrangements could vary. We had two main categories of isomers. One was structural isomers, the other was stereoisomers. We talked about the structural ones, including chain isomers, where the alkyl chains could be differently placed, or they could be different in lengths, which include methyl chains and mostly ethyl chains. Propyl or butyl chains were very rare. In position isomers, you have the same functional group in two compounds, like hydroxyl or like halogen, but the positions would change. In functional group isomers, the whole functional group would be different. We did some examples for chain isomers, then we did some for position isomers, and then we did some for functional group isomers. In today's video, we're going to be attempting some past paper questions to see our understanding of the concept of isomerism. This question says, how many isomeric esters, including isomers and stereoisomers, we're not going to be talking about stereoisomers, so I'm going to cancel it right now, can be made with the molecular formula C5H10O2 if methanoic acid is one of the two reactants used. Now remember, methanoic acid looks like this with only one carbon atom, and we have a total of 5 carbons, so total 5 carbons. Remember, the ester has this functional group. Now if methanoic acid is one of the acids used, we know we have to remove the OH from the methanoic acid. So what we can do is we can have a hydrogen here, which is methanoic acid wala portion, and now we can have the rest of the 4 carbon atoms in a single chain. So overall it's a 5 carbon molecule with ester functional group. It has 4 carbons on the alcoholic side and the 5th carbon is on the methanoic acidic side. So first ester can be drawn like this. The second ester could be drawn again with the same methanoic acid and oxygen here, but now you can have the carbons, let's say 3 carbons together, and fourth one could be a branch. So this way you can have CH2, CH, CH3, and then the branch would be coming from the middle carbon. This way, let's highlight it. You had 4 carbon branch, now you have a 3 carbon with a methyl group. Do we have any other possibility? That possibility would involve changing the methanoic acid, but we don't have to do that. So the two possibilities we have right now include a straight chain alcohol and a branched alcohol. We'll talk more about esters in the upcoming videos, but you get the idea of how we can do chain isomers. Let's go to a second question. It's a theory question. It says X is CH3, CH, then bracket OH, CH2, CH3. I want you to focus on this structure and realize that it is the condensed formula. It is the condensed formula because they are using a bracket for a branch. How many carbons are here? It's carbon 1, carbon 2, carbon 3, carbon 4. The OH is on carbon 2 because you can see it has only one hydrogen. It looks like this, a CH3, then a CH with OH because the OH is in bracket, which means branch, then another CH2 and then CH3. Carbon 1, 2, 3, 4. Pause the video and think about its name. Now I hope the name that you reached was butene 2-ol. It's butene 2-ol. Now where is the isomer equation? Read part B. It says there are 3 structural isomers of X that are alcohols. Draw the structures of these 3 isomers. Look at butene 2-ol. The first thing you can do is make a branch. So instead of writing the 4 carbons in a line, you can make a branch. How will we do this? Let's zoom in. You can have 3 carbons in a straight chain. The OH would still be on the second carbon, but now you can have first carbon, like the missed carbon, as a branch. This is your straight chain. This is your OH group, and now you can place the rest of the hydrogens. I am drawing the displayed formula, but you can choose to draw whichever formula you wish to draw. This is the structure of carbon 1, 2, 3. So you have 2-methyl, because there's a methyl on carbon 2, propane, 2-ol. This is the structure of 2-methyl propane 2-ol. Another thing you can do is you can keep the same structure but change the position of OH. You can still have 3 carbons, fourth one as a branch, but this time the OH can be moved to carbon number 1, or you can say from any side, because it would still be carbon 1. So it's a 3 carbon. You have CH3 on one side, CH in the middle, CH2, and then CH3 as a branch. I just wrote H's instead of drawing their bonds, but you get the idea, right? Carbon number 1 would be the one with OH, carbon 2 in the middle, carbon 3, and this is a branch on carbon 2. So you will call it 2-methyl propane 1-ol. This time it's not propane 2-ol, this time it's propane 1-ol. Do we have any other possibility? Sir, you can keep the main chain of 4 carbons, don't make a branch, and just remove the position of OH, like just move it from carbon 2 towards carbon 1. So don't make a branch, keep your 4 carbon chain, this is a 4 carbon chain, and put the OH on first carbon. So CH3, CH2, 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 carbon number 1, 2, 3, 4. It would be called butane 1-ol. So right now you have chain isomers and you have position isomers. These are isomers of butane 2-ol. Let's go to this question. I really like this question because it has also skeletal formula understanding for us. It says a new jet fuel has been produced that is a mixture of different structural isomers of compound Q. You can see compound Q. I'm zooming in. You can see that your main chain is the zigzag structure in the middle, and you can see all the other structures are branches. You can see 5 branches. Let's number these structures: 1, 2, 3, 4, 5, 6th, 7th carbon, 8th, and 9th. It's a 9 carbon structure. There's a branch on 2nd, 3rd, 5th, 7th, and 9th. It would be called 2, 3, 5, 7, 8 pentamethyl, because there are 5 methyls, pentamethyls nonane. Nonane is your longest chain. Nonane is your longest chain. I know it sounds a little weird. And then you can see there are 5 branches of methyls. Now we know how many carbons are here. 5 methyl is equals to 5 carbons. Longest chain is nonane, so 9 carbons, which is a total of 14 carbons in the main chain. Now let's go to each option individually. Let's go for option A. You can see your longest chain starts from the left and continues to grow like this. Remember, you have to find the longest chain. If you found the longest chain like this, that would be wrong, because then you would be missing on 2 more carbons. So your longest chain is like this. These are your methyl groups. Carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. There's a methyl on 2, 3, 5, 7, and then 8. I think it's exactly the same name, so they are identical structures. It's not an isomer, it's not an isomer because it's exactly the same structure. Now let's go for structure B. In structure B, the longest chain starts from the left, and the only possibility is the continuation that you can see here. Now, these are two branches, 1, 2, and the third one. The two branches are ethyls because they are double carbon branches. Let's number the main structure. 1, 2, 3, 4, 5, 6, 7, 8. It's an octane. There is a branch with ethyl, another branch with ethyl, and there's a methyl. So it would be called 3,4-diethyl. I'm also practicing the naming for you guys. So it's 3,4-diethyl. Then it's a 5-methyl octane. So 8 carbons because of the octane. Octane is equals to 8 carbons. 2 ethyls is equals to 4 carbon because each ethyl is double carbon. And there's a methyl, so 1 carbon. It's a total of 12, 13 carbons. Can't be isomers because carbon is not equal to 14. So B is not a good answer for us. Let's go for structure C. You can find your longest chain starting from the left. This is your longest chain. You can see a branch, another branch, 2 more branches, and this 1 more branch. Now, the naming of this structure would be a little difficult because this is a 3 carbon branch. You can see there are 3 carbons A, B, C. Don't worry about the naming here because now you can just count the number of total carbons. Starting from left, 1, 2, 3, 4, 5, 6, 7. It's a heptane with a methyl on 2, 4, 6, 5, and there's a 3 carbon branch which is a propyl. We don't have to do the naming here, but let's count the carbon. It's a heptane because of the 7 carbon chain, so 7 carbons. There are 4 methyls, it's a tetramethyl, so there are 4 carbons because of the methyl, and there's a 1 propyl branch, so 3 carbons because of that. A total of 14 carbons. It could be a very good answer for us. Confirm option D. We will have the longest chain from here because this way it is longer than any other possibility. Let's number it. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's a methyl on carbon 2, carbon 3, 5, 7, 8. 2, 3, 5, 7, 8. It's exactly the same name as initially. So this is also identical. Also identical. So D and A were bad options. B is not exactly the same carbon. C is the right answer. So C for catto is the right answer. I don't know why I call it catto. In this question, alkenes and cyclic alkanes should be considered. How many structural isomers of C4H8 are there? The first one I know is butene. I can draw 4 carbons in a line and I can have a double bond on the first carbon, first and second, and that would be called butene. But 1-ene. I'm not like drawing the hydrogens here, because right now my concern is just to show the main skeletal structure. You can say main structure. Another possibility would be but 2-ene. You change the position of the carbon-carbon double bond. It would be called but 2-ene. It's a position isomer. The third structure would be you make a 3-carbon structure with a double bond and make a branch. This way, it's not a 4-carbon branch. Let me show you. It's not a 4-carbon structure anymore. Rather, it's a 3-carbon chain with a methyl. It would be called 2-methyl but 1-ene. We can draw even cycles, but remember, while you draw a cycle, 2 hydrogens are already lost. So in order to draw a cycle, you lose 2 hydrogens, so don't draw a double bond. That is why draw 4-carbon cycle. It would be called cyclobutane and would have the same formula as a butene, because in cyclobutane you have the same kind of number of carbons of hydrogen, and obviously like number of carbons and hydrogens I meant. So cyclobutane. Do you have any other possibility? Think about it. You can have a 3-carbon cycle with a branch. So you can make cyclopropane and you can have a branch. This way you complete your carbon hydrogen requirement again. So this is your fourth and fifth possibilities. So there are 5 possibilities using alkenes and cycloalkanes. By the way, one thing, alkene is equals to cycloalkane in terms of formula. 1 double bond is equals to 1 cyclic structure. Let's do this structure. It says the question is about molecules with molecular formula C4H8O2. Give the structural formula of the pair of chain isomers, which means branching. Chain means branching. With the formula C4H8O2, there are carboxylic acids. So you know what are carboxylic acids? They have the carboxylic acid functional group. I'm drawing these functional groups in both boxes. In order to complete 4 carbons, 1 is already here. Now, so carbon 1 is already here. Now you can draw carbon 2, 3, 4 in a straight chain structure. Draw the hydrogens. So hydrogens would be drawn like this. 2 hydrogens on carbon 3, 2 hydrogens on carbon 2. That would be your butanoic acid. In the second structure, you can have a branch on carbon number 2. So carbon number 2 has a branch and it's a straight chain of 3 carbons. So it's a propanoic acid with a branch on carbon number 2. The names would be butanoic acid, and the name of the second structure would be 2-methyl propanoic acid. At the end of the day, they are 4 carbon structures. Question B part 1 says, give the structural formula of the pair of position isomers. Position means difference in functional group position. With the formula C4H8O2 that are esters. So we know ester functional group is C double bond O with 1 more O and C. C double bond O with 1 more O and C. Now if you want to draw esters, 2 carbons are already here now. Now we want to draw 2 more. So draw 1 here and 1 here. Draw the hydrogens. That is first ester with all its hydrogens and carbons. Let me make it a little smaller so that it fits in the box. Okay, perhaps we can't do that. And the second structure would be two carbons are already here, one, two. So now we can draw one on this side and then one, two. Let's that would be the same. So let's draw two on the right side and just one on the left side. No, that's the same. So this time we can flip it by like this. Nothing on the left side and three on the right side. Yes. So that would be a methanoic kind of ester. Draw the hydrogens. Yeah. Now this is your alcoholic portion. This is your acidic portion. In that case, in the first structure, you had two carbons on the acidic portion and two carbons in the alcoholic portion. Both are ester groups, by the way. This is ester group. In our upcoming videos, we'll be talking about esters shortly after carboxylic acid, so it will help us. In today's video, we tried doing some past paper questions drawing position, structural, and other kind of formula to understand the idea of isomers. In the next video, we'll talk about geometrical and optical isomers. Stay tuned, guys. Thanks.